Hi everyone, thank you for joining me this evening. My name is Lauren Harley and I work for Salmon Trout Conservation. If you haven't heard of Salmon Trout Conservation, we are a national lobbying charity and our ultimate aim is to get more wild fish in rivers. And a huge part of that is water quality, which is what I'm going to be focusing on this evening. Before we start, a little bit of a disclaimer. I'm not an entomologist, but I have worked on invertebrate-related water quality projects for SNTC for about 6 years. So I think I've picked up some bits and bobs. My talk is going to be three main components. The first component is going to be a little bit of background about invertebrates indicators and the sort of current state of rivers nationally. The second part is going to be a little bit more project managery about the nuts and bolts of SmartRivers, its scope and how it works. And then the final part will actually be some very exciting outputs from the data collected from the SmartRivers volunteers last year, and a bit about how once we have multiple years of data, it can be used to actually make a difference. So let's kick off. I'm going to start off with a bit of background about the state of our rivers and how the pressures that they're facing. As you've all probably seen in the newspapers and headlines and things aren't too brilliant. Nationally, only 14% of rivers in England are achieving good ecological status, and that's under a piece of European legislation called Water Framework Directive, which is meant to be in place to protect our water environment. Under that, none of them are meeting chemical standards, which is a bit scary. And recent assessments in 2020 have indicated that 93% of salmon rivers in England and Wales are classified as at risk or probably at risk. So moving on to chalk streams specifically, chalk streams are some of the planet's rarest habitats, and 85% of this world resource is actually found in England. 4 of these do have the highest protective designation available, which is the special area of conservation designation. But despite this, we are seeing worrying declines and trends in our own research. We did a piece of work a few years ago. We actually compared some of the invertebrate results we'd collected to records from 1998. And we did find up to 44% loss of banefly species in chalk streams compared to those records. So why is this happening? Why are we seeing these problems? So the simple answer is because pretty much everything we do on the land has a consequence for our waterways. Rivers carry the chemical and physical fingerprints of their local catchments. So when we take out water to drink, that's especially relevant for chalk streams. The way we use the land, we discharge wastewater into our rivers, we change the natural structure when we build on them. Our activities also spread non-native invasive species and contribute towards climate change. So a wide range of activities we're doing have a knock-on effect on what's going on in the river. So I'm going to just talk about a few of the pressures as a result of these activities. I'm going to start with sediment pressure. Now, rivers do have sediment inputs naturally. Sediment entering rivers is not a completely unnatural process, but it does become a problem when too much is entering our rivers, and our activities can exacerbate that load. When there's too much sediment in a river, that can smother river gravels, which can actually kill riverfly and fish eggs, destroy fish spawning habitats. So like when salmon are making their redds and laying their eggs, they need lovely, clean, oxygenated gravel. And if that's full of sediment, it's not really appropriate. The sediment can choke the submerged macrophytes, so like the ranunculus and the healthy river plants. It can also reduce plants photosynthesizing, because when there's a lot of sediment and it's disturbed, it can make the actual water column quite turbid. It can also stop invertebrates. It can get rid of habitat, because a lot of invertebrates live between the spaces between the gravel. So if those are blocked up, invertebrates can't live there. And sediment deposited along the riverbeds can actually change the flow regime and alter the habitat completely. And I've just put this little stat at the bottom that says 75% of sediment losses to the water environment are estimated to be from agriculture. So agriculture is kind of the key input for that. But some of the direct discharges do actually release sediment as well. Another one of the pressures is phosphorus. Now, we've probably all heard a lot about sewage recently and the impacts that's having. Phosphorus, again, is a natural component. It's a nutrient which is required for growth, for plant growth. But again, unnatural loads of this, too much of this from wastewater and agriculture is a problem. When there's too much phosphorus in rivers, it can cause blooms of nuisance algae. So this horrible green slimy stuff will cover the riverbed and it will remove oxygen from the water and again, block up that habitat and make it unsuitable for eggs and invertebrates. And this stat, 11 billion litres of wastewater are estimated to be discharged into UK rivers daily. And all of that contains phosphate as well as a bunch of other things. But not all sewage works are required to have phosphate stripping and have it all removed. So it is a typical component of sewage water. Another pressure we've been focusing on is chemicals. So again, from the sewage discharges, but also runoff from activities on land. So this can be things we apply to fields to prevent pests, so pesticides, but it can also be in sewage, in wastewater from pharmaceuticals, because everything that we put in our bodies comes out of our bodies and then it goes to the wastewater treatment works, and not all of it's removed. It can go straight back out into the rivers. And this can have some really concerning impacts. One of the particularly worrying ones for us as salmon and trout conservation is that it can actually prevent salmonids transitioning into their marine phase. So as smolts move down a river, the young salmon move down the river and transform into smolts ready for their life in the ocean, the exposure to some chemicals can actually mess up enzymes that they need to tolerate salt water, so it can weaken that transition and make them less successful and less likely to survive when they go into the ocean. It can also disrupt some natural biological processes, such as reproduction. Exposure to some chemicals can, you've probably seen feminized shrimp, crustaceans, things like that. It can also change their behavior. So it can change their feeding behavior, their mating behavior, and just make them do things they wouldn't naturally do. And we have more than 150,000 chemical substances in commercial use, with potentially several thousand added every year. So chemical loading is not going away anytime soon. Okay, and then finally, I'm just going to highlight flow. We call flow the master variable, as ultimately it determines the impact of the previous stressors. So more available water means inputs are diluted, and high velocity actually stops settlement of sediments on the riverbed. So flow kind of controls all of these things. So unpicking these water quality pressures is not a straightforward activity. Unlike land, where pollution is more localized, rivers are constantly moving and constantly changing, which makes detection of these pressures very difficult. The long-term sublethal impacts are also not obvious by eye. They're not something that you can obviously see. There are a few clues that if you're kind of looking into a riverbed, you can think, oh, actually, that might be a result of sediment pollution. But it's important to remember that if you take one thing away from tonight, take away that just because a river looks clear and it looks beautiful, the reality may be very different under the surface. So rivers can lie to us. It's sometimes there's some very bad secrets being concealed under the beauty. The pressures are also quite difficult and expensive to measure, so particularly chemicals, very hard to get the right lab tests to pick them up, and yes, they can cost a lot of money. The other main issue is that the pressures actually all act together. So in combination, they can exacerbate each other in a more than additive way. So phosphate and sediment are, they act quite closely together. One of them will bind to the other, and the impact of both of them together can be several times more dangerous than it would be if they were just acting independently. And further complicating matters is that because of the ever declining resources available to the brilliant people on the ground doing the monitoring, the coverage nationally, the resolution, and also the frequency of national monitoring regimes is kind of disappearing in front of us. So we've got a bit of a gap there. We like to use the phrase kind of death by a million cuts, so with rivers, because it is literally just this big pile of problems that are all mashed together, and there's no sort of silver bullet, and we all can just work at these one bit at a time, but we have to consider it all in together. So now we're going to move on to invertebrates. Where do invertebrates come into all of this? Now, invertebrates are the base of the food web. They're a food source for the things that we all enjoy: the fish, the birds, the bats, all of those things. But they're also key to ecosystem processes like nutrient cycling. So there's a reason our rivers aren't just full of dead leaves and organic matter. Invertebrates like gamma shrimp break these down and release the nutrients back into the river. Some are also ecosystem engineers, which means they actually change the habitat around them. So if we take the net spinning caddisflies as an example, these caddisflies make silk webs a bit like spiders, and they hold parts of gravel together. And by pulling this gravel together, they actually change the environment around them, and they can change flow and the way sediment is deposited. So they'd be classified as ecosystem engineers. So as well as their kind of essential ecosystem roles, invertebrates have other characteristics that are very useful to us. And the main one and the basis of SmartRivers is the fact that you can use them as indicators of water quality. And every invertebrate species has a very unique tolerance to different types of water pollution. So the pressures I've just mentioned. And the presence and absence of these different species can actually indicate what pollution a river may be experiencing. With nymphs, so there's some nymphs that can live in their water phase for multiple years. They are constantly exposed to the water and the pressures around them. And that can give us a much broader picture of the river health, as opposed to just getting a test tube and sticking it in the water and doing an analysis for one point in time. Now, before I go a bit more into using invertebrates as indicators, I'm just going to give you a very brief taxonomy lesson. So this is a kind of basic breakdown of how you classify all animals. It starts from the very broad kingdom classification all the way down to the very specific species designation. Now, I was taught in school to remember this with a mnemonic, and it was king penguins can only find green socks. Now, I like to think I remember quite a bit from university, but it's funny how things like that always stick in your head. Most of the regulatory monitoring done is to family level. However, the SmartRivers monitoring is done to species level. So think of it a bit like a supermarket. When you go into a supermarket, you have different categories, and then those are divided up by brands, and eventually you get down to the one product that you want. It's kind of dividing up animals in the same sort of way. So more on that later, but just bear that in mind, that essentially species is the highest resolution that you can get. So how does using invertebrates as indicators actually work? Well, you start with taking a representative sample at a river site, and then you identify all of the species there, and you'll end up with a big list, and that is the invertebrate community at that site. Now, every species has most species have a standardized value, and this tolerance value is for a variety of common water quality pressures. So this little table at the bottom is actually taken from the sort of sediment tolerance metric, and all of the species are categorized into groups. You've got A, B, C, D, and E, from highly sensitive to excluded. You find your species within that list, you look at how many of that species you have, and from that you can give it a score. Now, all of these values are combined, and then they're used to generate an impact value for that site. So you'll get an overall kind of sediment value for the site. And that has grading bands of impact. So it will go from unimpacted to highly impacted, like in a traffic light kind of system. And we can do that for many of the pressures, so sediment, chemicals, phosphorus, organic pollution, and flow. And you can put all of these together and come up with a water quality scorecard for a site. And to be able to do that, you just from having a whole list of invertebrates is really useful. Most of the species that score the best, they're highest water quality indicators, but also the least tolerant of pressures, are EPT species. Now that stands for Ephemeroptera, Plecoptera, and Trichoptera, essentially mayflies, stoneflies, and caddisflies. As a general rule, 20 or more of these species in your sample list indicates healthy water quality. In 2017, SNTC actually agreed with the local Environment Agency of a target of 10 mayfly species for the test in Itchen. So it's important to remember that diversity is key. We want a river with a variety of these animals, not just high abundances of one or two species. We want a nice big range of these different animals. Invertebrate species can also provide a lot of information around climate change. They respond to river warming in divergent ways, which makes them really useful for seeing how systems change as temperatures warm. Some can adapt and others will disappear. Loss of cold water loving invertebrates has already been documented in Scotland and Wales. Some mayflies can actually shorten their generation time and increase the number of generations per year in warmer climates. Baetis rodani is an example of one of those. And this table here is actually a study from the Upper Tybee, and it shows the temperature tolerance ranges of invertebrate species based on some modelling that was completed. So these bands against the list is the temperature tolerance range for each of the species. And every one of these has its own unique preference range. The blue section actually denotes the projected temperature range in the 2080s. But when you look at this tolerance data, you can actually work out what species may be lost as the river warms up, as the degrees go up. And that's particularly important to know, because as our invertebrate communities change, the rivers, there are knock-on impacts for other species. It affects all of the ecosystem functioning. So the fish and the birds and the bats, if you think about it, a lot of the predators, time bits of their life cycle in conjunction with emergences of mayflies, stoneflies. If those are changing because the species is lost, or they've adapted their life history strategy to emerge at a different time, then obviously the bird or whoever will suffer as a consequence of that. So where does SmartRivers come into all of this? Well, SmartRivers is using all of these things that I've just talked about. It's completing species level invertebrate monitoring with our lovely volunteers. It's an evidence collection project, and it feeds directly into our policy work to improve water quality. And we're using that species level analysis of invertebrates as a diagnostic test to better understand and manage and take action against water quality pressures. So this little flow chart here actually shows how SmartRivers fits in with our other work streams. The riverfly census is akin to SmartRivers. It's like its professional sister. It's all done by professional entomologists, and we'll actually be reporting on our riverfly census rerun, which we did last year. So keep your eyes peeled for that. But SmartRivers is the volunteer version, riverfly census is the professional version, and all the evidence collected from both of those projects feeds into our water action campaign. And that is using evidence to fight for water policies that are fit for purpose and properly enforced. So many of you on here are volunteers, and I'm sure you're already involved in the riverfly monitoring at the Anglers Riverfly Monitoring Initiative, so the Army monitoring, which is usually done once a month. It's a one-day training course, and the analysis is all done bankside into different groups. It's a brilliant initiative, and SmartRivers is actually complementary of that. SmartRivers falls under the Riverfly Plus umbrella, so it's not duplication of that effort. They do two different things. The Riverfly Monitoring Initiative will detect gross pollution incidents, so those larger scale, lots of things dying kind of incidents, whereas SmartRivers is this higher level, higher resolution. What are the problems? Where are they happening? Why are they happening? Look, it's all done with a microscope rather than just on the bank. So it's just going that sort of step further. So why bother? I mentioned earlier when I gave the little taxonomy lesson that we'd be touching on this again. So species level data can actually show far greater differences relative to family level data. For example, within the caddisfly family Hydrocycidae, they differ. Each of those species within that family differ considerably in respect to water quality, food, and flow preferences. We can even see differences at genus level. So genus was the step up of after family, but the one below species. Caddis from the genus Athrapsoides have been shown to have completely different responses to pollution effects when analysed to species level. So we go to species level because we think it's valuable to get that high level and really make the most of those invertebrate communities and all those differences. So now we're going to go into the project managery section. I'm just gonna have a sip of water. So apologies if any of you are already SmartRivers volunteers and know all of this, but for those of you who don't, I'll just give you a brief overview of how we set up SmartRivers hubs. So hubs are per river, and we set these up for groups of about 10 people. The Watercress and Winterbournes hub is a double hub, so it's all of this times 2. No prior training or qualifications are required, so anyone can participate. We start by choosing 5 sites which are a suitable habitat. They must be riffle glide habitat that's appropriate for the type of sampling that we use. They must be safe and accessible for volunteers. And we encourage the hub hosts to think about their questions. What do they want to find out? Are they wanting to investigate above and below a discharge, or above and below where they might be implementing some restoration work? It's just important to think about it in context of what you're trying to achieve. Again, as the Watercress and Winterbournes hub is a double hub, we actually have 10 sites rather than 5. The next step is to get a professional benchmark. So in the first year, once sites are selected, a professional will come in and do a spring and autumn analysis and do all of the invertebrate ID in a lab. And that provides a baseline for what we're working with from those sites. It gives us a kind of expected species list for training, because there are millions of invertebrates and we don't want to teach volunteers to have to identify all of them. So we give them a tailored kind of starting point to work with what to expect. And as they, as the years go on and they ID more things, we grow that list and they become more familiar with the invertebrates on their patch. Then we, usually in conjunction with the benchmarking, but it doesn't have to be, we run the training courses. Now, this is 2 days. The courses are certified by the Institute of Fisheries Management. And the first day is in the sampling technique. So we use the 3-minute kick sweep sampling technique, and we teach it to the Environment Agency guidelines. So a lot of time is spent on thinking about your available habitats and divvying up your time accordingly. The second day is on species identification and uses that list, that expected species list that I just mentioned. So you've got your benchmark, you've had your training. Then what do? Well, you can decide whether ID is actually your cup of tea or not. If it's not, there are options for the volunteer groups to send their samples away. But if they're really keen, we'll give you a microscope and you can ID them yourselves. If you want to do a bit of both, that's also fine, and you're not fixed into doing one or the other. You can pick it up and put it down as much as you like. And then finally, you're ready to sample independently. The volunteers go out twice a year, and you must keep your buckets for quality control. If you're doing identification yourself as a group, we do a professional analysis on 1 in 5 of the samples, and we will compare the list produced from the professional to the list you've ID'd and give you feedback and any help with any errors you might have made, any tips that we can give you to kind of improve your learning. The species found from the analysis are entered into our database, and that's how we get those stress signatures. So when I was mentioning earlier about the sediment table and how all the species have their own values, well, when you put the species list into our database, it kind of does that. It does that calculation, and then it churns out the values for each of the stress signatures. So who is already involved in the programme? The programme is pretty widespread. You can see the yellow dots from the very, very tip of Scotland on the Hallidale to down here. We have over 20 hubs established in England, Scotland and Wales. And one of these is our double Watercress and Winterbournes hub. The programme collected, didn't change that X to a figure. We collected over 200 water quality profiles last year. And those water quality profiles would never have existed without SmartRivers. We are very open with all our data, so it's all, anyone who wants to see it, we will share it, and happy to have a conversation about it. It's not a big secret. All of the hubs have a host organisation, and we have a really wide range of hosts. Some of them are wildlife trusts like you guys, but we also have water companies, fishery organisations, and some just really keen volunteer groups who want to be involved. So now we're going to focus a bit more on the Watercress and Winterbournes hub. The yellow dots actually represent the sites monitored by the SmartRivers volunteers. There's 10 of them across the Tessenich headwaters. They were benchmarked in 2018-2019, and the volunteer monitoring began in 2021. There was a little bit of a gap because we all know what happened in 2020. We have 1 season of volunteer results so far. I'm currently receiving autumn 2021 data at the moment. I've had 1 site in so far. The volunteers are still going through all of those samples. So what data are we actually producing from SmartRivers? Well, as we've mentioned a lot, the pressure scores. The pressure scores are in our free open access database, and you can interrogate that database. You can pick a time period, pick a pressure, and just see nationally how rivers are smart river sites are faring. There's that traffic light scale with you can see in the legend that will show you where the impacts are, and that gives you a really nice kind of catchment overview of where there's pinch points and where pressures are happening. We also have those full invertebrate species lists, and those themselves, those invertebrate records, are invaluable. And they are, such a useful tool to have for in the future, because, in 50 years' time, we won't be thinking, oh, what was there? And relying on that kind of anecdotal information that we have to refer back to a lot now. So having those high resolution species records is really beneficial. So now I'm going to give you all a kind of first preview of some of the preliminary results from the volunteer outputs from the SmartRivers monitoring. So I'm going to show you the 3 different pressures. We're going to start off with sediment pressure, and I've kind of split it into sections. So you've got the Anton Pill Hill Brook, the very top left, the Bourne Rivulet, the Upper Test, the Arle, the Cheriton Stream, and the Candover Brook, and that's where the SmartRivers sites are. So what we can see is that there's moderate sediment pressure quite frequently occurring at the KFC site, not so much at the Stanner site, and there was at the Abbott Sand site, but we haven't picked any up in 2021 so far. Again, will be interesting to see what autumn 2021 tells us. But yeah, definitely so far there's a bit of a pinch point around the KFC site. For Harroway Bridge and the Bourne Rivulet, seeing some sediment pressure there, but not so much downstream at Iron Bridge. At Polehampton, which is at the very top of the test, we're seeing some moderate sediment pressure, but not further down at Freefolk. Ingleston, things are looking okay. Cheriton Stream, we did pick up a signature in 2018, but nothing in 2021 concerning so far. And Boroughbridge is all looking good so far. So a bit of a disclaimer, when we're using biometrics, these aren't a kind of silver bullet output. These are indications. So when this is why we like to collect long time series, because when we have multiple records of seeing the same outputs coming out, it gives us more confidence in what we're seeing, and then that it acts as a flag for us to focus further investigation. So yeah, it's important not to put too much weight onto a one season signature. We do need that bigger picture and that longer time series. For chemical pressure, everything's looking pretty good. There were a couple of moderate signatures in the benchmarks, but nothing so far coming up. Again, we typically see more chemical impacts in autumn, and that's just because if there's been a dry summer, I mentioned flow is the master variable earlier. If there's less water, the chemical impacts can be more pronounced. So again, it will be intriguing to see what the autumn comes out with. Phosphorus pressure, again, in this spring 2021, nothing particularly concerning coming up so far. There were some moderate signatures in the benchmarking at KFC site and in the Polehampton site. So yeah, it will be interesting to see if we see any more of those trends in the monitoring going forward. So again, like that's just a few preliminary results. It's very early days. Once we have multiple years of data, we can actually move on to the more exciting bit, which is looking for those trends and possible explanations for what we've found. So this table on the left is actually an example from one of our SmartRivers hubs who have got this multiple year data set now. It's from the River Chew, so not a chalk stream, but you can actually heat map out over time where the pressures have been particularly worrying. So on this table, you can see at the downstream reservoir site, there's persistent sediment pressure coming up there. So now we are in conversations with the group to talk about why that is and work with the local stakeholders to try and figure out what to do about it. And on the right, this map is just a map of the land use around these are the 2 SmartRivers sites. And as part of the multi-year investigation and finding out the trends, we look at the land use around those sites. What's happening? Is it mainly arable land? Is it mainly urban land? Because again, that can help give us a better idea of what may be causing the pressures and where they're coming from. And yeah, we will be doing the same thing for our Watercress and Winterbournes hub when we have a bit more data. So for what can the hubs use the data for? I mean, we selfishly like to use the data for our national lobbying purposes. So the contribution to the national picture. We use your data as evidence to actually make water quality improvements and drive suitable policy and proper enforcement of those policies. But hubs, especially the hub leads, they are often organisations who want to do more projects around improving water quality, improving the river. So this kind of analysis actually gives a really good indication of where best to focus improvement efforts and where best to spend your money. It can pinpoint where your invertebrate communities are most stressed and by what is stressing them. It can also be a really useful tool in before and after restoration monitoring. If you're doing some in-river habitat work, if you've got SmartRivers monitoring before and after, you can actually see if there's any difference in the invertebrate communities, any reduction in pressure scores as a result of the work that you've taken. And yeah, that's me. Any questions, happy to answer them now.